Okay, let's start. So if we summarize our previous lecture, then in previous session, we have introduced damping the spring mass system. Then the purpose of damping is to resist the vibratory motion. So due to presence of damping, any mechanical system, we get reduction in the amplitude of vibration and natural frequency. This is what the significance of damping in any mechanical system, right? Then we have discussed about different types of damping. So we have discussed three types: viscous, Coulomb, and structural damping. So in general, structural damping is the property of material itself. Each and every material that is having its own damping property, and that is why we have discussed that cast iron is best structural material for machine tool compared to steel. The reason is cast iron gives good damping property, right? But the structural damping is very less compared to viscous and Coulomb damping. Viscous and Coulomb damping generally we are providing as an external damping, so that's why their magnitude is way large compared to structural damping. So in common problems, we generally ignore structural damping because it is very less, right? In this course, we'll be discussing more about viscous damping. So that's why we have seen principle of viscous damping by considering one fixed plate and one movable plate. In between these two, we are having some fluid whose viscosity is mu, and the distance between these two plates is small h, right? So then uh, we know, due to the viscosity, based on the Newton's principle, we know that tau is equals to mu dv by dh. dv by dh is the velocity gradient, because if you move from this fixed plate to this movable plate, then velocity keep on increasing and you get maximum velocity at the bottom surface of this movable plate. So that is what represented by this velocity gradient. Generally we assume this velocity gradient as a linear. Otherwise it's a non-linear, but the non-linearity is very less, so we assume only this as a linear. So that's why dv by dh we consider as a straight line, straight inclined line, right? Now this is what the Newton's principle: shear stress in any fluid is equals to mu is the viscosity and this is velocity gradient. Then this shear stress is experienced by this top plate, then tau is equals to F by A, force which is to be given to this plate for the movement, divided by area of uh, this top plate, right? So F by A, and based on that we have seen that F is equals to mu A by H into V, where this mu A H, that is what called as a damping constant, right? And this F is called as a damping force, amount of force required to uh, to give damping in the system, right? So Fd is equals to Cx dot. Now velocity is indicated by our general notation in this vibration course, that is x dot. So Fd is proportional to velocity through proportionality constant C, and C is depending on mu A by H. Now suppose if I want to increase damping in any system, then what I need to do? Either I need to increase mu, means I need to change fluid, I need to either increase cross section area A, or I need to reduce H. So by playing with this parameter, we can change damping constant of the viscous damping system, right? So this is what we discussed, and this is also called as a damping coefficient as well. So damping constant and damping coefficient both are same. Then after we have derived unit of damping constant, which is Newton seconds per meter, and then we have seen one spring mass system with the damper, and using Newton's approach we have derived governing equation of motion. So this is governing equation of motion of spring mass system with damping. So xt is equals to c1 e raised to s1t plus c2 e raised to s2t, and this s1 and s2 are nothing but roots of quadratic equation. So these are the roots, right? So till this we have discussed in the previous session. Now we are moving further today. So now what we are going to do, we are going to now introduce one another new parameter. Let me call that parameter as damping ratio. Now today we are going to discuss about damping ratio and three different cases of damping system. Today we will be discussing about damping ratio. The notation generally used is zeta. Now let me write this complete equation which we derived in the previous session. So x of t is equals to C1 is a constant e raised to, these are the root which I am writing, this S1 and S2. So S1 is minus C by 2m. If you have your lecture note with you of previous session, then you can keep open. So this will help you to understand. Square root 1 minus 4 km by c square, this entire into t, right? Plus root 2 S2. So C2 e raised to entire term as it is, only we will consider minus here, right? So minus c by 2m minus c by 2m, and then entire square root which is written here into t, right? So this is what the value. Now if we consider this term equals to 1, we call this 4 by km by c square, which is under the square root, is equals to 1. Then this type of system is called as a critical damped system. This type of system is called as critical damped system, where this value is equal to 1. And when this equals to 1, then this C, which is damping constant, is called as critical damping constant, right? So I call now C suffix C, where this C suffix C is called as critical damping constant, right? So, or critical damping constant or coefficient, both are same, right? So what we can say, Cc, if we go for cross multiplication, then Cc is equals to 2 square root km. This is what we can write, okay? So 2 square root km for our spring mass system, which we have assumed. Or I can also write this 2 square root k by m if I multiply and divide by square root m, right? Then what we get here, 2 square root k by m into square root m into square root m, then we get m only, right? And now we know what is square root k by m. Can you please revert what is square root k by m for any spring mass system? Janish, Karthik, Divyam, what is square root k by m?
Natural frequency.
Natural
Yeah,
frequency.
it's a natural frequency. So 2 omega n m. This is what the equation of critical damping coefficient. This is called as critical damping. So either this or this. Both are the equations for critical damping coefficient. Right? Now we'll see what is significance of this critical damping coefficient in today's session. So suppose next term is damping ratio. Next term is damping ratio. So damping ratio is indicated by zeta. Then zeta is equals to C by Cc. This is what called as damping ratio. Now what is Cc? As we have derived earlier, the Cc is critical damping coefficient. Critical damping coefficient, and this C is the external damping coefficient, right? This is called as external damping coefficient, and this is called as a critical damping coefficient. Okay, now for introducing this zeta in our governing equation of motion, we are doing some modification in equation. Here if you look here in this C by 2m, I am modifying that C by 2m equation. So if you consider C by 2m, then if you divide by Cc and if you multiply by Cc, then there is no change in the equation, right? But the C by Cc is now called as zeta, damping ratio. This term is called as zeta, right? And now let me write this Cc is what? It's a 2 square root k by m. So it's a 2 square root k by m divided by 2m. Then 2 will be cancelled out. Square root m divided by m. Then what we get? We get square root m. So finally, you get zeta omega n, right? So I can write this term as this term in our governing equation of motion here, right? So that is what we are doing now. Now again we are rewriting our governing equation of motion of spring mass system when damping is considered. Then x of t is equals to this above equation we are writing again. This equation we are writing again as C1 e raised to, instead of minus C by 2m, I am writing minus zeta, right, plus and zeta omega n as well, but omega n is present in both the terms, so we will be taking it common. So I am directly writing it's a zeta minus plus zeta square minus 1, and omega n is taken common from both the term and t time, right, plus second part is C2 e raised to, again same equation, but instead of plus now we will write second root, which is minus. So minus zeta minus square root zeta square minus 1 omega nt. So now we say this is our final equation of motion star, where we have written entire equation in terms of damping ratio, natural frequency, right? Now, we will see now what are the variations possible in this equation. We'll discuss now different conditions of zeta. So which are those conditions? Let me define those conditions. I can say zeta is equals to 0. This is one condition. Or I can say zeta is less than 1. third case is zeta greater than 1, and fourth case is zeta equals to 1. So these are the different possible variation in this zeta value. Either zeta is equals to 0, or zeta is less than 1, or zeta is greater than 1, or zeta is equals to 1, right? So one by one, we'll put this all conditions in this equation, governing equation of motion, right? We'll put this different condition. Now, first of all, simple case is, if you consider zeta is equals to 0, zeta is equals to 0 means what? If you look here, when zeta is equals to 0, when c is equals to 0, when c is equals to 0, when there is no external damping, right? Means you are not giving any damper to the system. Means our a previous topic, single degree of freedom spring mass system, free vibration of spring mass system without damping. So zeta is equals to 0 means there is no damping present in the system. This value is 0. External damping is 0, right? So if we do that, then what we get here, if I consider zeta is equal to 0, then I can say x of t is equals to c1 e raised to, now this is 0, this is 0, then what we get? We get minus square root minus 1. Square root minus 1 is called as I, imaginary part, right, into omega nt plus c2 e raised to, again this is 0 minus 0, then again imaginary part omega nt, but this time this is minus and this is plus. So this is what we got result when zeta is equals to 0. So this is nothing but undamped free vibration, undamped free vibration, which we learned earlier, right? But now, as we are talking about damped systems, so zeta should be in range of less than 1 to greater than 1, right? So now we'll consider different cases. First, suppose we take case 1, where zeta is greater than 1. So zeta is greater than 1. That type of system is called as a overdamped. Overdamped. Zeta is equals to 1 when c by cc is greater than 1. So that system is called as overdamped. So let me first of all write x of t, our governing equation of motion which we derived, c1 e raised to minus zeta plus square root zeta square minus 1 omega nt plus c2 e raised to minus zeta minus square root zeta square minus 1 omega nt, right? So this is what our equation. Now here what we are assuming zeta is greater than 1. So zeta is greater than 1, then look what will be the end result. If you consider zeta is greater than 1, then here we get some minus term plus zeta is greater than 1. So value more than 1 minus 1, always we get here positive value. So square root of positive value, that will give us positive value, but that positive value is actually less than 1. Are you getting or not? Suppose if I write here e, now here we get some negative value because zeta is greater than 1, so minus some value, right? Then if I add here plus, now zeta is more than 1, then from that more than 1 value I am subtracting 1, right? So always I get positive value under square root. So here again I get some positive value, negative value and positive value. But this positive value is less than this side negative value, right? So always e to the power will be negative value omega nt. Same will happen here on C2 as well. So C2 e raised to this negative, this negative, both will give you again a negative value, right? So which indicates that when e to the power means is the exponential reduction in the amplitude of vibration. That is what represented by this term. So if I indicate it on xt curve, xt diagram, this is time, this is displacement, then if any body is vibrating with some initial amplitude, then you get gradual decay in the amplitude, which is represented by this e to the power negative value. So this is what the gradual reduction in the amplitude, right? So when you consider overdamped system, means if your external damping value is more than critical damping value, then you get reduction in the vibration amplitude. And now this will not cross the mean position. It will just come and stop at the mean position here, right? So there would not be oscillation about this mean position. System will not vibrate actually. What happens, for example, if I am indicating it on spring mass system, so this is suppose spring, and then we have mass here. Now this I call x is equals to 0, mean position. Suppose I am moving this system up as it is shown here. This is mean position. But if I am moving this system up by some amplitude, now suppose new position of mass is somewhere here, right? Then as I release this, then due to overdamp condition, this mass come down to mean position and it will stop here. It will not cross mean position. Now, if you recall our earlier topic, undamped system, then due to inertia of this mass, it always cross mean position and that move to the opposite side, right? And we get some to and fro motion, but here will not get to and fro motion. That is why, that is because of presence of overdamped system, right? So there would not be any vibration. If you give any amplitude and if you release that system, then due to the overdamped condition, will not get vibration of mechanical system. So there would not be any vibration. So this is case one. If you go for overdamped condition, means here external damping is greater than critical damping. Now, what is meaning of critical damping? That we'll see here. Okay, now suppose if you wish to find out what will be the value of C1 and value of C2. If you want to find out value of constants of this equation, then what we do actually, we consider some initial condition. So two constants are to be determined. Then we need to go for two initial conditions. So earlier we have done this type of process to find out initial constants, where we have assumed that initial displacement at time t equals to 0 is suppose x0. Means at time t equals to 0, we have given some initial displacement to the mass. Similarly, I consider second initial condition, that at time t equals to 0, some initial velocity is also given to mass. Means I move this mass upward and then I also give some initial velocity and then I release system. So system will vibrate, right? So these are the two initial conditions. Just put these two initial conditions one by one in this governing equation of motion. Then that will give value of C1 and C2. I'm just giving you that task, or let me do that. Suppose if you consider t is equals to 0 and x of t is equals to x0. So look here. This is the equation of displacement. So it is x0 when t is equals to, put here t is equals to 0. If I put t equals to 0, then this entire term will be 0. Then what we get, e raised to 0, then that is 1. So we get here c1, right? Plus, same here, c2, e, t is equals to 0. Then again this e raised to 0, then we get 1. So this is, we got one equation. Now, we need to give this velocity, but we are not having velocity equation. So let us find out velocity equation from this displacement equation. So what we need to do to find velocity equation, we need to differentiate this by time. So let us differentiate it. X dot t is equals to c1 is constant. Now this entire bracket which is multiplied with t, that will come down because e raised to x, differentiation of e raised to x is what? With respect to t is x e raised to x of t, right? This is what the differentiation. So what happened now, this will come down. So we get here minus zeta plus square root zeta square minus 1 omega n. This entire will come down, and e raised to this as it is, minus zeta plus square root zeta square minus 1 omega n, right? Plus again differentiation of now this second term, same c2 minus zeta, but this time instead of plus we have minus, minus square root zeta square minus 1 omega n, and e to the power minus zeta minus square root zeta square minus 1 omega n, right? So this is what we can say our velocity equation. Now let us put the second initial condition. At time t equals to 0, velocity is x dot 0. So x dot 0 when t equals to 0. So this sum is as it is. So I write here c1 minus zeta plus square root zeta square minus 1 omega n, and e the power 0 then 1 plus c2 minus zeta minus zeta square minus 1 omega n, right? So we got this as a velocity term. Now two unknown and two equations, then they are easy to find. What we'll do now, instead of c1, just put x0 minus c2 in this equation and solve it. If you solve this equation, then you will find your value of c1 is equals to x0, and value of c2 is equals to x dot 0 plus omega n x0. You'll find this, right? So we got c1 and c2. Okay, so we got this c1 and c2. Now simply I need to put this c1 and c2 in this equation. Then we get our final equation back, right? So this is how we can find out this constants of equation by giving some initial conditions. So these are the in general initial conditions. Here given both velocity as displacement. Earlier in our previous lectures, we have seen one by one also, like t is equals to 0, displacement is given, there is no velocity. When t is equals to 0, velocity is given, no displacement. And when t is equals to 0, velocity as well as displacement, both given. So this is what we have seen that case with damping. But this type of case earlier also we have solved. Now, this is case, next case is when zeta is equals to 1. Zeta is equals to 1. Then this is called as critically damped system. critically damped system, right? So critical damped system, then zeta is equals to 1. If you do that, you keep zeta is equals to 1, then let me again write that equation which we derived so far. So this is in general equation for spring mass system with damping. So again I am writing that entire equation once again. Plus 2 is 2 minus zeta minus square minus 1 omega n, right? Now what we assume, zeta is equals to 1. To do that, you put zeta is equals to 1, then see c1 e raised to minus 1 plus zeta is equals to 1, so 1 square minus 1 0, so this term will become 0, and now we get omega nt multiplied with 1, so we get minus omega nt, right? C1 e raised to minus omega nt plus, do same again for C2, so C2 e raised to, again what happened here, you get this term 0, then we again get here minus omega nt, so here we are getting C1 e raised to minus omega nt plus C2 e raised to minus omega nt, both the case minus omega nt, then I take that common, then C1 plus C2 e raised to minus omega nt, but I cannot do that. Otherwise this C1 plus C2 becomes a new constant. You might learn this part in your previous semester in numerical method course from mathematics. We cannot do that. We need to consider some different solution. So that's why you might have seen this type of problem. If this happens, then we need to consider uh, one coordinate time t about which I am differentiating this equation, right? So this will be the solution. Now this will be the governing equation of motion if we assume critical damped system when zeta is equals to 1. Zeta is equals to 1, then this equation is modified as this equation. Otherwise, in when zeta assume as greater than 1, then we got this type of equation. Zeta is greater than 1. Zeta value is greater than 1, right? Now here also what happened? If you consider critical damped condition, then again we are getting this is the one constant value we can say, and e to the power minus omega nt. Then here also what we are getting, if I plot it on x t curve, time to amplitude curve, then here also when you release system after disturbing it, then again we get decay, and this is because e to the power minus means we are moving down, we are getting reduction, right? And it's an exponential, so we get curve here. So this curve is representing this value, and this x is representing this value, right? So it is decaying and it will not cross mean position, so again no vibrations, there will not be any vibration, right? So if you consider zeta greater than 1 to zeta equals to 1, then in this range there is no vibration. This body will not move to and fro, means it will not follow sinusoidal curve. Otherwise, so far how we are presenting vibrating body, we are presenting like this. But if you consider zeta greater than 1 and equals to 1, then body come to mean position and it will not cross the mean position on the other side. It will just come and rest, right? So that is the effect of zeta. If c by cc ratio is greater than 1 or equals to 1, then we get no vibration, and that is what the significance of critical damping coefficient. If c equals to cc, means external damping is equals to critical damping coefficient, then system will not vibrate, right? So if your requirement is to not allow any vibration, then you need to give external damping equals to critical damping of that system. So if I again write what is equation of critical damping, it's a 2 square root km. For spring mass system, what is k and what is m, how much value, just find out that value. So that value, suppose I am getting as for example 80 newton second per meter, right? This is what cc for particular system, that is what we are assuming, right? अब हमें ये सिस्टम को वाइब्रेट नहीं होने देना है, तो हम क्या करेंगे, वी नीड टू सेट एक्सटर्नल डैम्पिंग c equals to 80. If you do that, then there would not be any vibration. Now we know this c is depending on so many parameters which we have learned in the previous session. C is depending on mu ah, and c is depending on mu ah. Then set this value such that you get c is equals to 80. Then if you put that type of c value, then there would not be any vibration in the system, right? So we have seen three cases today for zeta. When zeta is equals to 0, then that is undamped system, means there is no damper. Then we discuss about zeta greater than 1 and zeta equals to 1. I hope it is clear why this cc value is important, because if you set c equals to cc, then there would not be any vibration in the system, right? So